feeling about these ramp problems? Things were starting to make sense, but now I'm confused all over again.
Yeah, especially figuring out the components.
And what's with the axis being tilted like this? It just looks wrong that way.
I remember the professor said that it's because it makes the calculations easy. It turns a two-dimensional problem into a one-dimensional problem.
But even if we use a rotated set of axes, there are still forces in the y direction.
Right. There are forces pointing in the y direction, but there is no motion in the y direction.
Oh, that makes sense. With the tilted axes, the net force in the y direction is 0, so there's no acceleration in that direction. The only acceleration is in the x direction.
Do we know it's accelerating, though?
Oh, right. It is possible that the box won't move at all.
Well, yeah, that. And it could be moving with constant velocity, so in that case, there'd be no acceleration.
But either way, whether there's acceleration or not, the box can only move in the x direction. Okay, I guess it makes sense to use the tilted axes.
Let's do an example. I need to practice or else I'll mess up during the exam.
Good idea. This one sounds simple enough. A box slides down a 12-degree frictionless ramp. The ramp is 3 meters long, and the box is initially at rest at the top. What is the velocity of the box when it reaches the bottom?
So, the box will speed up as it slides down. The steeper the ramp, the more it'll speed up.
Right, gravity is causing the acceleration. But since it's not in free fall, the acceleration must be less than g. We should check that later.
The next step is the free body diagram. There are two forces acting on the box. One is the force by the ramp, and the other is the force of gravity. Anything else?
I don't think so. The box is interacting with two things: the ramp and gravity via the earth. There's no friction in this problem.
Okay, let's add the tilted axis now.
The normal force, the force by the ramp on the box, is already in the y-axis, but we need to find the components of the weight in this tilted axis.
Let's see. This angle is 12 degrees.
How do you know that?
Well, they're similar triangles, so they're going to have the same angles, and this one is clearly the smaller angle in both triangles, so they have to match. And the larger one is 90 minus 12.
Are you just eyeballing?
Yep.
Give me a minute, I need to convince myself. If you extend this line, you get two similar triangles, which makes this 78 degrees. And these two lines are perpendicular. So if this is 78, then this must be 12. I think I get it.
I just know that one of the angles in the free body diagram is also 12. And with such a shallow angle, it's easy to see which one it must be.
Okay, I understand. But what if it's not easy to tell just by looking at it?
I just draw a very shallow ramp on the side, so I can see where the angle is.
Oh, I like that. Let's compute the components of the weight in the x and y directions. So Wx must be W sine 12, and Wy must be W cosine 12. And just to check, sine 12 equals Wx over W. So I think we got it right.
And since the net force in the y direction is 0, we know that Wy is also equal to the normal force, and that the net force in the x direction is Wx. This is the part of the weight that accelerates the box down the ramp.
So the masses cancel out, and we get that the acceleration of the box down the ramp is equal to g sine 12, which is clearly less than g. That makes sense.
It's only a component of the acceleration due to gravity, the component in the direction of the ramp.
Right. And I think that now we have everything we need to solve for the velocity at the bottom of the ramp. We just need to use one of the kinematic equations.
Let's use v final squared equals v initial squared plus 2a delta x. This way we don't need to compute the time it takes for the box to reach the bottom. So v final squared is equal to 2a delta x, because the initial velocity is 0. So v final squared equals 2 times 9.8 times 3, and taking the square root, I get that v final is 7.67 meters per second.
Hold on. Wouldn't 7.67 be the velocity if the box was in free fall? Shouldn't we use the acceleration we computed before?
You're right. In that case, the final velocity is 3.5 meters per second. Not as fast as if it was in free fall.
Which makes sense. You want to try adding in friction to see how things change?
Sure. Let's draw the free body diagram with friction. We still have the normal force and the weight, But now we also have a force of friction pointing up the ramp.
Kinetic friction if the box will still slide, and static if it stays in place. Let's do the situation where the box will slide.
The net force in the y direction is still 0. The normal force is still equal to Wy, which is equal to W cosine theta. The net force in the x direction is what accelerates the box down the ramp. In this case, the net force is Wx minus the force of friction. And the force of friction is mu times the normal, which is mu times W cosine theta. So max equals Wx minus mu W cosine theta. Max equals mg sine theta minus mu mg cosine theta. And finally, the acceleration is g times sine theta minus mu cosine theta.
And that makes sense because the acceleration will be smaller than what we had before. It's like the friction is taking some of it away. I think that's enough for now.